All right, in this exercise, we will be exploring deep sea habitat based on particular organic carbon that is raining down from the surface. And I'm just going to start with our biogeography exercise code here and just modify it here a little bit. It'll make it a little bit easier. So I'm just going to put this exercise. We will be loading 11 years of annual particulate organic carbon. This is in milligrams per meter cubed. Estimated by the NASA MODIS Aqua satellite. All right. We will use these fields to create an environment for the deep and thick habitat. So we're going to adjust the paths to reflect the location of not SAT data and R data, but this is now going to be POC data .R data and bathymetry.R data. So here's our libraries are going to load again. And here is our load function. I'm just going to replace SAT data here with POC data. Does that load? Yep. And this one's going to be now bathymetry.R data. So this is the file of ocean depths. This is in meters. So we'll run those two things. Good. We look in our environment. Got bathymetry. Again, lat long. Here's our POC array, very similar to our chlorophyll array and SST array that we had before. Now it's just particular organic carbon. Again, we're going to transform our POC like we did. Well, we're going to transform it in the same way we transformed chlorophyll, log 10, converting POC values. That should be meter cubed. All right. And now we're going to just do a quick example of the bathymetry and POC data. So let's just go ahead and put in here, it's called Bathymat. Don't need a time. This is going to be depth in meters. Let's go ahead and run this. Give ourselves a little more room. All right, there we go. So here is the depth of the ocean. You can see where the mid-Atlantic ridge is. It's a little shallower. And we've got some really, really deep spots here in these trenches, these really dark blue. All right, so that's so far so good. And now let's take a look at our POC array. Log 10. Oh. Okay, let's take a look at this. Did I not run the log 10? I should have. Let me try loading this again. Load them, transform it into log 10, and come back down here. There we go. Looks similar to chlorophyll, not exactly the same. So this is a derived product from a satellite. They're trying to guess how much particular organic carbon is sinking down into the deep sea. All right, I'm going to take this out. I don't need this. In fact, we might take a lot of this out here. Yeah. Oh, and I'm going to rename this. All right. So we borrowed a little bit from the biogeography exercise. Now we're going to kind of go off on our own here. So we need to combine our POC and our bathymetry data. But if we take a look at the dimensions of the bathy matrix, it's 1080 by 540. And we want to use the Martin curve eventually to use depth to help compute how much POC is hitting the bottom. But if we look at the dimensions of our POC array, it's 1080 by 540 by 11. So this has 11 slices or 11 arrays that, or 11 matrices that are 1080 by 540. This one's just 1080 by 540. So we're going to go ahead and just make the bathymetry matrix match the dimensions of the POC matrix. So what we're going to do here is create an array of repeating bathy mat. This is only to make the equation below easy. Okay. We just want them to have the same dimensions. When we add the arrays together, we always want them to have the same dimensions. So our bathy array, and then we're going to use the array function. So here's our matrix that we're going to put in there. And we want the dimensions of our array to be 3 elements. Again, 10, 80, 540 by 11. That should do it. So that should basically take this bathy mat and replete it 11 times. So if we look at the dimensions of array, yep, sounds good. All right. All right. Now, the other thing we're going to have to do, if you remember with our Martin curve, it assumed that the POC values were below 100 meters. So they didn't, the depth values less than 100 meters didn't work out so well. So we're going to take our bathy array and just eliminate or turn them into NAs. We're going to eliminate the I'm going to use replace here. Right, let's take a look at a picture here. I'm going to take about anything that is less than 100. So let's replace bathy array where bathy array is greater than minus 100 with NA. Take out all the really shallow stuff. And you'll see if we do it. Let's go ahead and put the lawn lat in here. Oh, I just have to do the first. Ooh, this is now 11 slices of it now. So let's do one of them. Okay. You can see a little difference here. All right, so you can see if we scroll back and through, so this part of the Bering Sea has been taken out. There's a couple little coastal areas that we've been taken out. So if I just toggle back and forth, hard to toggle. You can see here our original plot we had it there, but now we're just dealing with really deep ocean. greater than 100 meters. All right. Now we are going to apply the Martin curve following Miller 13.25 in your book, Charlie Miller's book. So this equation assumes that the POC data is at 100 meters depth, which is a big assumption for derived POC. And okay, let's see what we can do here. So bottom POC, how much is hitting the bottom? Bottom POC equals our POC array. That's how much is going in. And we want to compute depth, although we need to put in now our depths. And the equation assumes they're all positive, so I'll just take the absolute value of it. Divided by 100. This is coming right out of your lectures and the book. And I'm going to raise this to negative 0.82. And where did I get that from? So the exponent of the Martin so we had Miller had different exponents for different parts of the world, and figure 13.25, I'm just taking an average of those things. All right, so let's go ahead and run this. Nope, I want this to be POC. So again, we've got those 11 years here, so let's do a quick image plot of long, lat, so that is how much is reaching the ground in log units. All right, so up here quite a bit, down here not so much. Out here in the middle of the ocean, not so much. All right, so remember the units of this thing. Equation are log 10 POC in milligrams per meter squared now, because it's hitting the bottom. It's a flux across the bottom. Okay, so for these 11 years, let's try something. Let's take a mean and a standard deviation of the settled organic matter over the 11 years using the apply function. So this is kind of nice. Show the apply function. So if we want to do the mean bottom POC, so the mean over time. So if we take 1 pixel here and we take an average of those 11 years, we're going to apply bottom POC, and then the next argument is what's called margin. So we want to preserve margins 1 and 2. which is 1080 by 540, and we're going to average over the 11. Average over the 11. So we're going to preserve margins 1 and 2. We're going to take a mean. Oops. That's not what I wanted to do. Take a mean and ignore the NAs. Oh, somehow I deleted my margin argument. So if you look at the apply function, you'll see that what are you operating on? That's this thing. What margins are you working on? That's the next argument in here. What function are you using? Mean, and then ... You can add optional arguments, which is this na.rm. Let's do this again. All right, so the dimensions of bottom POC now are 1080 by 540. So we're back to just one average. Let's now do the same thing for the standard deviation. We can just copy this. Let's compute the standard deviation for it. All right, all done. Okay, so we've got the mean bottom POC at all these different depths. Actually, we can just do a quick image. And this is what it looks like. This is the mean. So we have shallower depths, we have deeper depths, but since we also have a matrix of depths, remember the Martin curve is a plot of how much is getting to the bottom versus depth, we can plot the Martin curve. This is going to be a plot of the mean bottom POC versus Daffy map. So we want XLab to be log 10 POC in milligrams per meter cubed. And our Y lab is going to be depth. It's going to be a lot of numbers. A lot of points that get plotted. Yeah, there it is. Yeah. So this is log 10 POC. Here it is. We still have that nice sort of exponential, even on log scales, right? So coming down. So this is our Martin curve for the ocean. All right, and why is it variable? Well, it's because we have different starting POC values, different parts of the ocean. And now let's go ahead and do a just did that. Take this. All right. And I'm going to borrow from our image.plot up here. Go and take this part. This is log 10 POC squared. Yeah, there we go. Okay. And let's do now the same thing for standard deviation. Standard deviation. Yeah, so we might need to change the z-lim here. Let's try from 0 to 0.1. Right now we're going up to 0.7. Yeah, you can see some variability there. Maybe it's in the ocean, 0 to 0.2 maybe, 0.02. And now we see some variability in here. Okay. All right. Let's now plot. Oh, we can also add a nice map. Should do that for both of these. Yeah, okay. Always looks nicer. So let's plot now relationship between mean, benthic, POC flux, and the standard deviation of the benthic POC flux. So if it's high, is it variable? If it's low, is it variable? So let's go ahead and make a plot of this. And that's our x value, SD. This is in milligrams per meter squared. My lab is going to be just this. That's going to be the standard deviation. All right, there it is. So here's the mean versus the standard deviation. So it looks like as the mean goes up, it becomes more variable in general. But let's go ahead and let's calculate. Let's go ahead and calculate the median, mean, bottom, POC. A dot equals true. Let's see what is the average in here somewhere. Is it just a whole bunch of points on top of each other? What's the median value? 0.823. So 0.08. So that's like down in here. And how about median? .002. Okay, so most of the points are down here. There's some that are over here, but just to give you sort of the median of these distributions here, I put it on this plot, which is always important. When you see a plot with lots of points like this, it's hard to tell where the middle of the distribution is here. Let's go ahead and do points. Our x value is going to be this. Our y value is going to be this. Color is going to equal red. Point character equals 20, which is a solid point. There it is. That's the middle of the distribution. So a lot of points down here. A lot of them down here. All right. So for the rest of the exercise, I'm going to go ahead and point you over to the homework where you're going to be asking the question about the intermediate disturbance hypothesis, whether or not the POC flux could help us test that hypothesis. All right.